Hey guys, what's up? Today I'll be talking about derivatives, except I'll only go into a very small part of derivatives. It's such a great part of calculus, and there's a lot to discuss. It's a very big topic, and it's obviously way more complex than what I'm going to discuss here. And so I'm just going to talk about the oversimplification of it, and I'll only consider some simple functions. So obviously, if you do not know functions, you have to learn about those first. And there might be a video coming up soon on functions as well. So hopefully, those who are watching can go and check that out. But first of all, I want to say derivatives are just the slope. So we know that the slope is represented by m, which is y2 minus y1 over x2 minus x1. This is the same as change in y over change in x. And we know that derivatives is just the slope. So in other words, derivatives is just change in y over change in x. And we know this if we take a simple graph here, we measure this line, which would be y equals mx plus c. Simple linear equation with a power of 1. Yeah. So the slope would just be, if we grab any y point here and any y1 point, so y2, y1, we would follow through and grab the, x here, sorry, x2, x1, we would grab the same y2, y1 points, and using these points, we'll be able to find the slope or the derivative of that line here, that section here. But also, even though we're grabbing the same point here, the derivative or the slope is the same throughout because it's a straight line. The change here is the same as the change here, which is the same as the change here, same as the change in smaller increments. And so this seems simple, as your constant here could be a simple, your slope here could be a simple constant like 3x. And so your graph would look something like this. Let's see, and go up like that. Right. So for y value of 1, or x value of 1, you will get 3. A y value of 2, you'll get 6. Blah, blah, blah. You guys get the idea. However, it's not so simple if your curve is, for example, a quadratic. So in this case, you would have a curve something like this, right? I'll take the simple quadratic of y equals x squared, right? Well, here we know that the derivative, for example, at any point, actually, if we say the derivative or the slope of this function, for example, but there's no easy way to put it. The slope just is not constant. It's not the same as a line, right? The slope is not changing. This change in y, for example, here, the change in y here might be more or less than the change here, for example, or the change here. As you can see, it goes up like that. It doesn't stay straight the same. So you would say, in other words, that the slope is changing. And so you can't put a single constant number. Your slope cannot be like 4 or 3. Because depending on where you are or what point you're at, your slope changes. So your slope would kind of be like a miniature function. So if you found the derivative, which I won't go into too much detail about how you find it, the derivative of this function here, this quadratic here, I'll just make a little arrow. The slope function or derivative function is y equals 2x. So let's say you're looking at the slope at this point here, which will be x value of, let's say 3. The slope here is actually a straight line, because we talked about this, right? The slope is a straight line. It would be a straight line which touches the point at exactly one single point. It touches the line y equals, I'll actually name this f of x, right? So when f of x is equal to y at the point where x is equal to 3. So this means that the derivative at that point is completely different than the derivative at 4, because at 4 it would be sloping upwards more. If I don't know, it's kind of hard to see on the whiteboard, but it would be a completely different derivative. So using this function that we found of x squared, we would plug in y equals 2 into 3 to find the slope, which is 6 at that point. So m value is 6 at that point, 3. At 4, well, it would be 2 into 4, for example. And you get 8, and so on. And so, well, the derivative, the simple rule to derivatives, especially for exponents, like x power 2, is just x power 2. If you notice, it becomes 2x. And if you see a pattern, it's that 2 goes down. But there's more to it. You see, x power 3 becomes 3x squared. X power 4 becomes 4x cubed. And so using all of this, well, I mean, obviously there's more proof to it, which is called first principle derivatives. And well, if we go past that, which is obviously way more complex, we can see that the simple rule to differentiating any function, an exponential function, is just nx power n minus 1. And well, I guess that works for cubic functions. It works for quadratic functions. Quartic functions, quadratics. It works for linear as well. And well, yeah, that's your introduction to or oversimplification of derivatives. One more thing before we end. You guys might have seen what I won't draw an equal sign. I'll rewrite it here. The derivative is also denoted by dy over dx. And I just want to get this in quickly. The change here, change in y over change in x, is just kind of rewritten. So the d means the exact same thing. It's the same, almost the same as the triangle, but it's denoted differently because it's not perfect. It's not exactly accurate when you're talking about derivatives, because it's not really the same as change in y over change in x. But yeah, it's more complicated. There's more to it, and there's a whole separate part called derivative first principle derivatives, and that's basically like where your understanding of derivatives really begins. And so this is just like a rule of thumb for exponential functions, which is, I guess, it's useful when you're going into derivatives. And so, well, other than that, I will thank you guys for watching. Like and subscribe, all that. Yep.